Thank you everyone for zooming in and making time for this webinar today. We had around 300 people register for this webinar, so we know there's a lot of interest in the potential of fusion energy. Next slide, please. I'm Doug Vine, the Director of Energy Analysis here at C2ES. I'm very excited about this technology. Frankly, I'm in awe of this technology and excited to moderate this panel. But before we dive into the content of today's webinar, let's just take care of a couple of housekeeping items. First, the webinar is being recorded and it will be posted to our C2ES YouTube page as soon as, typically about a day or so after the broadcast. Also, because we have so many participants, we're going to use the Zoom webinar chat box for audience questions. You can submit your questions at any time, and I will raise them as time allows to our panelists after the moderated discussion. All right, let's get on to the webinar. So I'm going to kick things off with a quick introduction to C2ES and why we're interested in fusion energy. Next, I will introduce our panelists from the Fusion Industry Association, from Commonwealth Fusion Systems and the White House Office of Science, Technology and Policy, who will deliver some short presentations. And this will be followed by a moderated discussion, and then we're going to take a few audience questions. And with that, let me quickly introduce my organization, C2ES. Next slide, please. Great. C2ES is now in its 24th year, and we are an independent, nonpartisan, nonprofit organization focused on strong policy and action to address climate change. Our core mission is to forge practical solutions to reduce greenhouse gas emissions, expand clean energy, and to strengthen resilience to climate impacts. We have a long history of bringing together diverse stakeholders and producing accessible content and publications to help advance climate solutions. Next slide, please. So we know from climate science and from numerous reports that we need to reduce emissions dramatically, aiming to become carbon neutral economy-wide by mid-century, so that we can begin to mitigate the impacts of high greenhouse gas concentrations in our atmosphere that are causing the climate impacts like heat waves, droughts, crop failures, heavy precipitation events, sea level rise, ocean acidification, and so on. To decarbonize, there are three equally important efforts that we need to be undertaking simultaneously. First, we need to make buildings, transportation, and industry as energy efficient as we possibly can. Second, we must transform the power sector by deploying massive amounts of transmission and distribution infrastructure to enable massive amounts of clean electricity generation, including renewables, energy storage, nuclear, and fossil fuels with CCUS. Finally, at the same time, we need to be transforming end uses away from fossil fuels to electricity where we can. We need electric cars and trucks, converting homes to electricity, for example. And where we can't easily do that, we need to switch to low carbon fuels like hydrogen or biofuels for harder to electrify applications. Next slide, please. So as I just mentioned, the power sector is going to play a strategic role in economy-wide decarbonization. And while there are many possible approaches that could achieve decarbonization of the power sector, most studies suggest that the least costly and the least technically challenging path to achieve the mid-century goal, net zero carbon dioxide emissions economy-wide by 2050, it involves having a diverse mix of resources, including not just renewables, such as wind and solar, but also firm, low carbon generation that can be dispatched on demand and for long periods of time. So resource diversity is key and optionality is key. Fusion power plants will be capable of providing firm, low carbon power available on demand around the clock, which will provide an excellent complement to increasing levels of renewable power generation. Fusion can help increase the resource diversity, and all from a reasonably small footprint. Next slide, please. So to build on those points, I'd now like to introduce our first panelist, Andrew Holland, CEO of the Fusion Industry Association. Andrew has worked at the intersection of science, energy, policy, and politics for 2 decades. In 2013, he authored the report Fusion Power, a 10-year plan for American energy security. Prior to leading the FIA, Andrew led energy and climate work at the American Security Project. And he's also a Hill veteran, serving as Energy Environmental Policy Legislative Assistant to US Senator Chuck Hagel. Andrew, take it away.
Great, Doug, thanks. Great to be with you all. Great to be here with C2ES. It is a real pleasure and honor for me to be at a C2ES event. I'm a longtime fan, as they say, longtime listener, first time caller, right? So it is an important part of the institutions in Washington leading to the decarbonization that our economy needs. So thank you for the invite and thank you for doing this. The Fusion Industry Association is only a year old as an independent nonprofit institution. We are organized as a 501c6 business association. That means we are similar to things like the Chamber of Commerce, the Solar Energy Industry Association, American Clean Power Association, such like this. We are the unified voice of the private fusion industry. And we are excited to be leading the way to clean, safe, sustainable fusion power. Next slide. And we're excited to be a part of this as a climate solution and to be talking through all of the options here. We are working to get fusion commercialized at speed. Just as a quick note here, if you do have scientific questions about anything I say here, I'm happy to set up talks with any of our member companies or anything like that. I'm not a scientist. As Doug said, I'm a policy and politics wonk. So next slide. Let's start with the basics. Why fusion innovation? Don't we have the tools for decarbonizing energy now? We just heard, Doug gave a whole list of great options that are out there. Solar, wind, advanced fission, all of these things. Well, fusion is uniquely suited to the rapid scale up that will be necessary to address climate change and bring affordable energy to the world. Fusion energy is reliable, firm power that will replace fossil energy sources such as coal and gas, while acting as an excellent complement to renewables, wind and solar that will dominate the grid of the future. Fusion's already generating green jobs in science and manufacturing today, and this will expand really exponentially as the industry grows. And I think an important part that has been underlined over the last several months is that fusion will break the geopolitics of energy so that a country's destiny is not determined by the size of its hydrocarbon deposits or its mined rare earth minerals. Putin's invasion of Ukraine really underlines the importance of energy geopolitics. I think it's a good point that he wouldn't have done that had he not felt secure in his dominance of energy towards Europe. Next slide. So fusion is closer than you think. Scientists have been working on fusion for more than half a century, enabled by DOE funding here in the United States and funding around the world by governments. But often we hear, but where is it? What's been going on? Well, you can see that the real advances made in this graph, put together by Sam Warzel and Scott Shue from ARPA-E, you can see these steady technology advances over time towards break-even fusion energy. Those lines at the top are break-even fusion energy, and as expressed in the NT-tau, the triple product, so-called, as it gets closer and closer to there over time. And you can see this is a number of different technology approaches, whether Tokamak, inertial fusion energy, and various others over time, getting closer and closer. The progress towards triple product was really at an exponential pace. But cost and complexity acted as a barrier to net energy. But now you have to add the wider technology revolutions in our society, advances in material, computing power, advanced manufacturing technologies, and that puts us on the cusp of a key milestone today, net gain energy, more energy out than in, sometimes expressed as Q greater than 1. We will see that milestone hit, and I believe so soon, whether it's the National Ignition Facility in California or a private approach like Commonwealth Fusion Systems joining us today. We're talking in the years, not decades timeframe. And the combination of technology revolutions and scientific understanding will enable us to put that milestone into a commercial package. And that's why you've seen the explosive growth in private fusion industry over the last few years. The skeptics who joke 30 years away and always will be simply haven't tuned in to the advances of the last few years. Next slide. And let's talk a little bit about the breakthroughs of 2021, because 2021 was really a milestone year here in fusion energy. I mentioned the National Ignition Facility. In August of last year, they achieved in a single shot 1.3 megajoules of energy out of it. And it was the first time that there was a burning plasma. And that's important. What that means is that the plasma itself provided the heating for the fuel, not the external driver, in that case, the lasers. A real milestone, and we expect to see further milestones coming from the NIF soon. Second, most powerful large magnet in history was built at CFS, and you're going to hear from Jennifer a lot more on that, so I'm not going to spoil the surprise. But there was record energy produced on JET, the Joint European Torus, over in Oxford in the UK. That announcement shows they held the plasma in place for 5 seconds, showing that basically that we have the technology to hold plasma for as long as we need to. And then finally, 100 million degree plasma fusion relevant conditions was achieved by 2 private companies, Helion and Tokamak Energy, last year. So that's an important milestone as well, that this is not something where the private companies are here to draft off of the back of the government programs. We are moving as well. So next slide. So that gets us into what is the private fusion industry. The global fusion industry in 2021, we did a survey last year, about this time last year, second quarter, and the numbers that I'll give here are based off of that. I should note that we're in the process of doing our updated fusion industry in 2022. So watch this space. We expect it to come out in early July or so. We could verify 31 private fusion companies around the world. 27 of them are members of the FIA. 21 of those companies were American. So notably, this is an American-led industry. The numbers on funding are important to note as well. Based on the Q2 numbers, we had 1.87 billion invested in private fusion over the entire lifespan. Of course, about 2 weeks after we launched this report, several of our companies made big announcements as well, which meant that 1.87 billion has more than doubled to over 4.3 billion by 2022. CFS was one of them, as were Helion, General Fusion. Just a tremendous time for the private sector investment coming into this. A couple other things to note. They focused on electricity generation, 96%. The vast majority of companies are focused on this as the key early market, and commercialization by the 2030s. I'm going to go into those both a little bit more. Next slide. The target markets for fusion, like I said, electricity generation. Fusion energy will ultimately enable a revolution in all energy uses, but the primary market that private fusion is aiming for is electricity generation. But other notable areas of interest for our member companies include clean hydrogen and ammonia production, even zero carbon shipping. You can put a fusion power plant on a large ship, and that takes away your maritime emissions issues. Fusion, the key part of this, though, is fusion will enable the deep decarbonization across the economy that we need. Next slide. And I want to note a bit of a surprise when we did this survey. The private sector approach has enabled a broad diversification of technological risks by having companies take multiple different approaches to fusion. Unlike the global government-funded approach, which has repeatedly cut technologies and moved forward towards one way, there is among our 27 member companies, there's really no overlapping technological approach. They're competing across multiple parallel pathways: magnetic, inertial, magneto-inertial, electrostatic, and more. And this is what happens when investors accept technological risk in the search for innovation and speed. And a bit quick slide here. Next slide, please. A bit to note, this is our current membership. As I said, 27 members. You can see more on our website, fusionindustry.association.org, including links to all of their websites and details about each of those companies. Next slide. The private fusion is really accelerating on a timeline. I want to talk a bit about the timeline here because everybody always asks this. When will you come? When's fusion coming? Most important takeaway from our survey was this accelerated timetable, because it's demanded both by investment schedules and also by the increasingly urgent needs of the climate crisis. Timelines here are indicative and common across the industry, but of course, there's some variation. So right now, thanks to the decades of scientific research into fusion, design and construction of breakthrough experiments is ongoing by private fusion companies. And this will result by the mid-2020s in fusion devices that will achieve a scientific proof of concept, scientific break-even, or the equivalent proof to move forward. Once successful, these companies will then move into building and operating pilot plants, scaling up supporting systems in the balance of plant, and ultimately a rapid global deployment of fusion energy by the middle of next decade. This is a decadal timescale. It is aggressive, but it is doable. And I think a key note would be to think back to that slide on the membership, 27 companies. Now that means that there's 27 shots on goal. Am I going to tell you that all of them are going to come? But they may not, but certainly with that many shots, you're going to get there. And for those of us who always accuse fusion of overpromising, let me make clear that fusion innovation is a function of both time and money. Fusion is hard. Fusion will always be hard. And it will be 30 years away if no one invests in it. And that's why the catalyzing effect of private investment has been so critical. This is really driving this time scale forward, really changing the game here. And we're excited to be a part of it. So next slide. Now with that, and I'm pleased to have Sally Benson from the White House here with us as well. I want to run through a few high-level policy recommendations. Sally's heard this from me already, but we do have specifics of fundings asked to Congress and the White House and such that you can find on our website. But today I'm just going to give you some top-line details on how to do a serious acceleration of fusion energy. And then I'll be done. Next slide. So first, we need a real partnership with DOE. The private industry cannot exist on an island separate from the national and global scientific program. U.S. fusion program must have a comprehensive energy mission, and that's why we're so excited about the White House bold decadal vision, which was announced at a March 17th event that many of us were at the White House for commercial fusion. And then we do need direct federal support for private fusion. We've seen similar support go to advanced fission, to the hydrogen economy, to various others. You know, we have not, and of course, the solar and wind and the subsidies they've received over the years. Fusion should be supported in a similar way. Pilot plants are built by the private industry, but public-private partnerships will enable the acceleration. And then finally, a note on regulatory certainty. Fusion is safe. We have shown that it's safe. Ensuring that fusion power plants are subject to appropriate risk-informed regulation will accelerate investment and development. I'm happy to go into any of these further in question or answer. Next slide. Just to say thank you, thanks to C2ES, thanks for you all for being here. You can go to our website if you're interested in joining as an affiliate member. Or we're open for educational and research partnerships as well. So thanks to C2ES. Back to you, Doug. Thanks. Look forward to your questions. Doug, you're muted.
Okay, just a little technical glitch there. Thank you so much, Andrew. That was a fantastic overview. And to help us put a finer point on the remark that Andrew made, that fusion is a lot closer than you think. Next up, we have Jennifer Ganton, who is the Chief Movement Builder at Commonwealth Fusion Systems, which is an interesting title to be sure. Jennifer leads a cross-functional team at CFS, helping to grow global support for fusion energy. And prior to joining CFS, Jennifer served as Vice President of Federal Affairs and International Market Expansion at Bluebird Bio. And she's also spent nearly 20 years with Chevron, working on critical policy issues, including climate change and environmental, social, and governance issues. Jennifer, you have the floor now.
Thanks so much, Doug. I really appreciate it. And I'll wait for my slides to come up. Great. So I want to thank C2ES also for inviting us to be part of the conversation today. It's a really exciting time for fusion energy. And I'll just say, Andrew talked about this a lot, but CFS is I'll talk a little bit about us as a company, but we have a belief that we've really, we're at a moment in time that is an important one for fusion, where there's some game-changing solutions that are here. And we as a company are building on traditional approach. You'll hear me talk about Tokamak during my presentation and the design that we're using, but married with some novel technology that has really only reached industrial maturity recently, which is what has changed and why we're on a path, the fastest path to commercial fusion, and we're looking to have our pilot plants on the grid in the early 2030s, as Andrew outlined. And that will really change everything in our mind. So next slide, I'll talk a little bit about the company. So Commonwealth Fusion, we refer to ourselves as CFS. We were founded in 2018, and the company was spun out of MIT at that time. And it's built on decades of research that had been done at MIT. But as I mentioned, there was a discovery of a novel technology, and I'll talk about it later, that impacted the magnets that we were able to use in fusion. And so on that idea and on that belief, we were able to spin out, have our own individual company, and we're closely collaborating with MIT, the Plasma Science and Fusion Center still today. But we've built a team of over 250 employees. We have a high caliber workforce that comes from not only sort of innovative and startup companies such as SpaceX and Tesla, but also, we're looking to build a company that can build at scale fusion devices. So we're also have employees that are joining us from more traditional companies like an Amazon or Boeing or those type of companies. But Andrew talked about the capital coming into the market. We've been with the magnet demonstration that we had earlier this year, we did our second raise of $1.8 billion, and we are now in a position where we've raised more than $2 billion to position us to build our net energy demonstration device and move towards putting a pilot plant on the grid. But I think the thing of note for us is the diversity of our investors. It's not just traditional venture capital, but we've also seen companies such as Google come in. We have endowments, we have pension funds. So it's really a diverse set of investors, including energy companies that are looking at the energy transition. So that's a little bit about CFS. We'll go to the next slide. So this slide, there's a lot of different data out there that talks about what is the challenge and what is the issue. But fundamentally, as we think about why now is the time for fusion, this graph demonstrates that there's going to be tremendous growth in the renewable sector, and we'll continue to see that. But if we're going to truly deeply decarbonize, there needs to be innovation. The world needs a fundamentally new source of clean energy in order to get to that 2050 net energy goals that most of us have set out. And this is really an unprecedented transformation. So next slide. So here, how do you fill that gap? It's a big gap. It's tens of gigatons that we're talking about, right? So how do we fill that gap? Well, you need an energy source that has zero emissions, can be delivered very quickly, is replicable, so you can manufacture it, is very power dense, has low land use, can work with existing infrastructure, all those type of things. So the graph that we have on the left is the growth of industry. So the black lines are things that have happened, and the orange line is how do we get and meet that challenge? And you can see it's a very steep curve, it's a log graph. So we've seen tremendous growth through wind and solar, but what we really need for a solution to fill that challenge that I highlighted earlier is something that can meet these criteria at the growth that is indicated here on this graph. So the next slide, please. We believe fusion is one of the key sustainable energies that can meet those criteria. So a little bit of this goes to what Andrew talked to, but fusion is a dispatchable source of high heat quality. And so we think about what is the commercial opportunity for fusion. We have the ability to repower existing power plants. We have the ability to go beyond electricity. And so while we are putting our first power plant onto the grid in the early 2030s, and we'll be demonstrating how we can generate electricity. There's lots of other sustainable energy applications that we'll be considering and thinking about as we scale our industry, and some of those are listed here. And I think they're very important as we think about getting to net zero. It's beyond electricity, but electricity clearly plays a really important role. So next slide, please. So one of the things as we think about how do you when you're developing a commercial business, you have to think about sort of how does this work? And the important parts of what fusion is and why it is so disruptive, and we think it will be able to meet that challenge that I've outlined, is it has zero emissions, it's power dense, it's dispatchable, it could be baseload power. It's inherently safe with no meltdown, no long-lived nuclear waste, no proliferation. We've done the work to determine that with the technology advances that we have here at Commonwealth Fusion, it will be economically competitive. But most importantly, it needs to be scalable. And so you need to be able to build it anywhere, have an inexhaustible fuel supply, leverage existing infrastructure. So the demonstration here is to show the fusion device. That's a picture of our ARC, which I'll talk about, our pilot plant that we're going to build. But it's being able to take that, that heat and convert that into electricity is going to be an important part of how we solve the solution is provided here. But we're going to have to build up an ecosystem around this to develop these, but we want to leverage the existing infrastructure, which is a really important part of the technology. So next slide, please. So here, Andrew had a different chart. There's a lot of different charts here, but the reason I put this one into my my presentation is I mentioned earlier, we're using Tokamak as the design for our device. And so here we put a chart in that shows we are very close. There are 35 companies or more in the sector. There's billions invested into the sector. But the design that we chose for the basis of our demonstration plant, Spark, and our pilot plant, ARC, is a Tokamak. And here you can see that it's really, there's a lot of proven science that sits behind the Tokamak design. There are many of them, and they've gotten very close. And we think we're on the cusp of Q greater than 1. But some of the technology that we've developed will enable us to move past and break through that barrier and have a net energy device. But we're standing on the shoulders of giants. Many people who've done work in Tokamak design and science and able to leverage a lot of that learning. Next slide. So here, this is where I sort of introduce our first sort of product. We had the opportunity to think about what would be commercially relevant in energy. And the magnets that were discovered while our co-founders were still at MIT and then spun out on building this technology, we put together a plan to develop and test this new novel high temperature superconductor magnets that would enable a stronger magnetic field. And why is that important? That's important because if you're able to shrink the size of the Tokamak, you're able to do it less expensively, and we have high confidence that it will work on the physics that is based on many of the other Tokamak designs, including ITER, which is a government multi-government project currently under construction, but be able to do that much smaller. And so this was really a breakthrough moment using these industrial materials that are only recently available and creating a magnet and testing that magnet to demonstrate a 2 times higher greater field, magnetic field for a fusion magnet than we'd ever seen before. And that gives us a confidence that we are able to build the spark device, which you see on the right, at 40 times smaller than the size of ITER, to demonstrate net energy with our spark device. So next slide, please. What we did is we were developing and testing the magnet as we were moving forward, but we knew we had high confidence, and so we proceeded with purchasing some land in Devens, Massachusetts, and we are building a magnet factory, which you can see in the background here, where we're going to build all the magnets for Spark, which will be on the site, and then that magnet factory will be available to build magnets for our future products, our ARC, our pilot plant, and ARCs down the line. And the foreground that you see there is the footprint of Spark. The Spark device will be built on this campus as well, and that is fully under construction. And this picture is already a week or 2 old, and the walls are already up around the Spark Tokamak Hall. So it's a very exciting time to be bringing this new high temperature superconducting magnet technology to the market, but also to be able to see the progress that we're making in bringing Spark. And if you can go to the next slide, I'll talk a little bit about what comes after Spark. So as we did we were building the magnet and getting ready to test it, and we were forging ahead with getting our campus ready and designing and building our Spark device. We're already thinking about ARCs in our fusion pilot plants. And this is a picture of what an ARC would look like. This is the rendering of the first pilot plant that would go into the grid that would create electricity into the grid. And so that gives you a sense of scale with the person next to it. So if you can go to the next slide. And as Andrew pointed out, we're on a timeline that's a fast timeline, but relevant to climate change. And that's what's important. We know we need to be fast, and the private sector is the place to do that. And so we built and demonstrated this novel magnet. People said it might take 10 years to do that, and we did it in 3. And now we're building Spark, and people thought that would take decades to move forward, and we will be launching Spark, and it will become operational in 2025. And that will be the device that demonstrates net fusion energy, Q greater than 1, that more power out than goes in, so that you know that you can have a design that is relevant to creating electricity. And then we have here early 2030s is we have high confidence that we'll have an ARC deployed, a fusion pilot plant, and that will be connected into the grid and be able to demonstrate that you can provide fusion power into the existing infrastructure today with an eye that the design of this device will be 200 megawatts of electricity or higher. So that is a quick overview of CFS and what we're doing in our timelines, and I'll be happy to answer questions at the end.
Thank you so much, Jennifer. That just looks like an amazing technology and an amazing company to be working for right now. So let's just turn our attention quickly to our third panelist. We're very pleased to welcome Dr. Sally Benson, who is kind of leading the administration's support for fusion energy. And Andrew alluded to a summit that was held at the White House just a couple of months ago. Let me just give you, Dr. Sally Benson is the Deputy Director for Energy and Chief Strategist for the Energy Transition in the White House Office of Science, Technology, and Policy, or OSTP. Dr. Benson trained as an earth scientist and engineer. She's an expert on a wide variety of topics related to energy and the environment. And for the past 25 years, she's focused on deep decarbonization of the global energy system. She comes to OSTP from Stanford University, where she is the Precourt Family Professor of Energy Resources Engineering in the School of Earth, Energy, and Environmental Sciences. So Dr. Benson, please share your opening remarks with us.
Okay, all right. Well, thank you very much, Doug, and Andrew, nice to see you, and Jennifer as well. So I'm going to be talking about our interest in fusion energy, and in particular give you a report out on a White House summit, developing a bold decadal vision for commercial fusion. But let me say a minute about what my role is. So of course we're all aware that the climate change problem is urgent, and the president has made commitments to 50 to 52% reduction in greenhouse gas emissions by 2050. 2030, and net zero by 2050, and 100% clean electricity by 2035. So all of you who are involved in the energy space know that that's sort of the blink of the eye in infrastructure time. So rightly so, the administration is heavily focused on deployment of the technologies that are available today: wind, solars, EV, batteries, heat pumps, and so forth. But at the same time, we're deploying like wild, like crazy, that we also need to be thinking about making sure that we have all the technologies we need to get to net zero. So that's my role here at the White House as the Deputy Director for Energy and Chief Strategist for the Energy Transition. So to say a little bit about context, so I arrived in Washington in September, and actually that was sort of fresh on the heels of some very exciting announcements. Andrew spoke about them, the very successful results at NIF. CFS had just had their first battery test, which proved that they could make a 20 Tesla battery, very, very exciting. And then the jet results followed shortly thereafter. And all of a sudden it became clear that fusion energy, which many of us had always sort of jokingly said was 40 years in the future, all of a sudden maybe that wasn't true. And the question became is what should and could the United States be doing to accelerate the development of this critically important technology? And what could and should we be doing to make sure that the US leadership is established in this technology that we've been investing in since the 1940s and 50s. So that sets the stage for the work that we have done. So if you can move on to the next one. So you've heard this, that we're on a very rapid path to net zero, and again to net zero emissions. That's what the graph on the right-hand side shows. So you can see that period between now and 2030 is a critical period where we want to reduce our emissions by half and get to zero again very, very quickly. Now, if you think about the energy system that we have today, was really, in the late 1800s, early 1900s, where some of the core technologies, being able to have coal-fired or gas-fired power plants and building a grid that provides electricity to nearly every home in the United States. So all of this took a long time. And so again, when we look at this very short time period, it suggests that the more that we can have technologies that can kind of slot in as replacements for existing technologies, such as you could replace a coal plant or a gas plant with a fusion plant or fission plant, that these are the kind of opportunities that are going to make sure that we can stay on track. And again, you've heard the need for this, clean, firm power. Again, renewable generation is fantastic. It's, when the sun is shining and the wind is blowing, it's the lowest possible cost. But what many authoritative studies have shown is that the lowest cost grid, the most reliable grid, is the one where you have a diversity of energy sources that taken together can deliver this very low cost, very high quality power. And so we see clean electricity and fusion as a critical element of being able to meet our net zero goals. And again, we were leaders. The United States, if you look at solar panels, wind turbines, lithium-ion batteries, the fundamental scientific discovery work took place here in America, but we are not the world's leaders in manufacturing, so many of those jobs are other places. We want to make sure that this time that American leadership in this technology is cemented. So moving on to the next slide. Again, you've heard this several times that we need this mix of electricity. I just thought you might be interested in this particular graph on the right-hand side, which is a product that was prepared by the Climate Policy Office together with the State Department that underpins our strategy for getting to net zero emissions in the electricity sector in particular. So the first thing, our goal is to have net zero electricity by 2035. and we're going to be able to do that. We will do that. So then the question is, well, where does a technology like fusion come in, which may not really be ready to scale until 2035? The reality is even after we have purely clean electricity, we are probably going to need to double or even potentially triple the size of our electricity system, as many of the applications where we directly use fossil fuel, like heating, like industrial processing, like transportation, as we begin to electrify those, even beyond 2035, we're going to need more electricity. Again, a key place where fusion could play an important role. So moving over to the next one. Thank you. Okay, so we got very interested in this technology. We began to engage with the Department of Energy, absolutely a fantastic partner, and together asked the question, well, could we accelerate the development of this technology? And we began a set of stakeholder engagement. First through many one-on-one conversations, eventually leading to our White House summit. So next one, please. So one of the things we were absolutely delighted by as we talked to our colleagues here in the White House and on the Hill and in the agencies, what we found is actually very broad support. And this is a picture of the keynote speakers, most of them, minus two who not there in time for the picture. But again, Gina McCarthy, the National Climate Advisor, Jennifer Granholm, Dr. Nelson, our own head of OSTP, as well as the Bipartisan Fusion Coalition. So, and Brenda Mallory, the head of the Council on Environmental Quality, all came together and said, if this technology is successful, could be something that would be very beneficial, and we support this. So next one, please. Okay, so the other thing that we had in mind for this event was, so often when new technologies are developed, the sort of public is left by the side of the conversation. And we decided, if this technology is going to scale quickly, if we're really going to pave the path to commercialization, we need to have an inclusive community. So, and we need to think about it's not enough just to get the technology right, but from day one, we need an inclusive approach for technology development, where we engage the community, the environmental justice community, and so forth. And we need to make sure that this is a bipartisan or apolitical strategy, because of the huge benefits it could have to the United States. Next one, please. So we had three specific announcements. Basically, the Biden administration announcing that it was going to take these concrete steps to develop and implement this vision. And as part of that first action, we were delighted that the Department of Energy created a new position that would report directly to the Undersecretary of Energy. And that's Scott Sue, who will lead this effort, and I know he's working hard as we're talking. And then finally, there was some increases in funding to further expedite the development of this technology. Next, please. So it was also very important to make sure that this was built on a very solid scientific foundation, that we really were ready. And what we heard from this amazing panel of leaders in fusion technology, that the time is now, that we are ready, that the fusion science community has come together and spoken with a single voice, that we're ready to move fast. So that was extremely important. And also we had someone from the private sector there as well, addressing the issue of how do you engage the utility industry early enough, again, so that when the technology is ready, we're ready to make those grid connections. Moving on to the next one. Second panel, as I mentioned, we really wanted to hear from representatives from stakeholder communities, And one of the quotes I like so much is, what if every time we developed a new technology, every time at the launch of this, we had this same kind of inclusive conversation? How just would our society be? And we got lots of specific advice of how we can move forward in a constructive way to make sure that technology is welcome in communities and that people understand it and feel comfortable with it. So moving on to the next one. Okay, and then of course, in many ways, the stars of the show, we're so excited about the vibrant private sector community of innovators and investors. And it's quite extraordinary how much attention this has gotten. And it's also really rewarding to see the tremendous success that many of these individuals and companies have had. But we all have to remember at the end of the day, this technology needs to compete with other technologies that are cost effective, reliable, and so forth. So we have a doubly hard mission to not only make sure the technology works, but it can compete in an open market. Next, please. So anyway, we were absolutely delighted with the summit. We got real action on the ground. The Department of Energy is building out its agency-wide fusion initiative. There'll be an event coming up in June where there will be a deep dive into public-private partnerships to figure out how to make these work for everybody. And we're just really excited. Now is the time to act boldly and let's make this technology a reality. So thank you very much.
Thank you so much, Dr. Benson. It's great to see all the support for from the administration for decarbonization and fusion in particular. So just sticking with you for a moment here. So historically, the US has invested a lot and we've been a technology leader in basic science research for various energy technologies. Yet, seemingly in many of the cases, we are not the technology leader in terms of having the manufacturer or being the manufacturers of the technology here in the US. We're importing solar panels and wind technology from overseas. Do you see that fusion could be different so that US companies could be more part of the full commercialization process?
Yeah, I think absolutely. And I think it starts with the strong private sector interests that we see today. I mean, all you had to do was look at those photographs of, putting, cement and steel in the ground. That's evidence of real commitment that we didn't necessarily see in some of those industries. The other thing is that I think we understand much better that we need to, again, pave the path to commercialization. We need to make sure that the regulations are in place when the technology is ready, and there's real progress already. The Nuclear Regulatory Commission is undertaking investigations. We also need to make sure as we start to scale up that there are resources available to build the factories, to create the supply chains. And we now have the Loan Program Office within the Department of Energy that is there and ready. So I think that we are, awareness was the first step that we need to do something differently if we're going to have these technologies be commercialized here in the United States. And that second, the pieces are falling into place. And so I'm very optimistic. I think that together with the Department of Energy's new fusion coordinator will, always have his eye on the goal and be there to course correct as we go forward if we're seeing that we don't have all the pieces in place to make sure that these efforts are successfully commercialized here in the United States.
Yes. So Jennifer, just bringing you into the discussion here. So Fort Devens is not a far off remote community. It's about an hour outside of Boston. And it's great to see all the development of an actual project underway. So how was it that CFS was able to gain community support and to get this project off the ground?
Yeah, thanks for asking. And we've just had I would say, a fantastic experience with the local communities around us and with the state of Massachusetts and the efforts there. And as you mentioned, Fort Devens is a redevelopment economic zone. So we worked closely with Mass Development to identify the site and identify the ability to move very quickly to build our factory and put this Spark Tokamak there. One of the things that we did was we realized there's a lot of people don't know a lot about fusion, right? And so there may be confusion. They may misinterpret and think it is confuse it with fission, or they may just not, they wanted to know and learn more, we suspected. So I apologize, it says internet unstable. I hope you're hearing me. But we went out very early to the community.
We can hear you fine though.
Okay, great. Yeah, we went out very early to the community and engaged. We held public meetings where we were available to talk to the community and educate them on fusion and what we would be doing. We did a lot of outreach to the environmental communities and built relationships with local environmental organizations here in Massachusetts, as well as the national level, to help them understand what we were doing, and very transparent and very open about the process and what fusion was and what we would be doing on the site. And once we were able to tell the story and build the understanding, I think the community and the state of Massachusetts is very excited to be at the forefront of fusion and have what we will call a groundbreaking, game-changing technology in their backyard. And so it's been just great working with them.
So I was curious, so the state of Massachusetts, have you been able to take advantage of any existing policy that they have? They're pretty, you know, a leader in emissions reductions and climate change. Have they supported you in any way or through policy?
At the moment, we're very aligned with the goals, a lot of the climate change goals, not only in Massachusetts, nationally. Our mission is aligned with what we're trying to do. And so, but we're very fortunate. We're a private company. We've been able to fundraise based on the demonstration of our technology, so that we have not needed to move forward with any. We've been able to move forward with Spark, but we do continue to work with the government here and the government in Washington. I think Andrew can probably talk to this about what would it take to bring fusion to the grid fast as possible, and what type of support is there. And so there's ongoing discussions which are more at the national level around milestone-based cost share programs for pilot plants and those type of things. We've seen some great advancements. The White House support has been extremely helpful, so thank you, Dr. Benson, and your whole team. But we've seen good progress in Washington, but we have more to do there. And Andrew, I don't know if you want to talk a little bit about that.
That's a great segue. Do you want to pick that up, Andrew?
Yeah, absolutely. So the Milestone Program and the broader public-private partnership that we're trying to build. We do have a big workshop coming up in a couple of weeks. The Department of Energy is hosting. Excited to lay out, kind of put some meat on the bones of what the bold decadal vision looks like. And a key part of that, we think, is this public-private partnership that will allow private companies to apply for and receive on a merit-based program government dollars to help accelerate their move towards proof of concept machines and ultimately towards pilot plants. This is something that was talked about in the National Academy's report, in the community's plans. It's really an important thing. We look at, if you look at something like SpaceX, which came to become private launch, it was supported in its early days by NASA in this milestone format, which means that when you meet a milestone, you get paid for performance. It's a way to protect taxpayers and incentivize speed. And we think it's a good model. There's other models as well. The ARDP program in advanced fission is showing an important way forward as well. So some of the details will be laid out in this June meeting. We have certain things to go forward to as well there. And yeah, we've also got a June NRC meeting as well. So we've got a lot of upcoming stuff here in early summer. Yeah,
that's great that this is all moving forward and getting kicked off. I there's been a lot of questions from the audience, and I do want to, touch on a couple of those. So one area that, and they tend to be more technical questions that people are asking. So, and you had mentioned in your opening remarks, Andrew, about not being reliant on your endowment of fossil fuels or critical minerals. So what are the issues with regard to the fuel for fusion? So what is the fuel that's used? Is it difficult or costly to produce in the quantities that are needed? Is it challenging to store the fuel? And how do you make it? What's the source material that you use? So just a real simple question.
Yeah, so very basic. It's the key thing about fusion is taking light elements and putting them together at extreme temperatures and pressures to make slightly heavier elements. So the sort of common pathway which CFS uses is two isotopes of hydrogen at extreme temperatures. They fuse together and form helium, and that helium and a neutron, and and a tremendous amount of energy. This is literally the power of the sun. So bring it down on Earth, put, kind of the common way to say it is a sun in a bottle. And so the deuterium is one isotope that's widely available, easy to get out of seawater. Tritium is the other one, and tritium does not exist naturally on Earth. It is a fuel source that when we get to a commercial scale, every commercial scale fusion power plant will have to make their own tritium. And you make tritium, it's a scientifically known thing. You make tritium when that neutron hits the lithium wall. And then there has to be a fuel cycle, and you have to control it. And I did see a couple of questions in the chat there as well about safety, and I think it's important to line this up as well, because tritium is a radioactive isotope, and so, but it's not something that we don't know how to do. The Canadian nuclear power plants can do reactors, produce tritium all the time, and we have a lot we can learn about safe handling of tritium from them. And this is a known thing that has been around for a long time. So it is, we do have to handle it right, and we have to make sure that we mitigate risks, and we have to make sure we do it in public. And so I'd invite, actually, I mentioned that NRC meeting. You don't have to take my word for it that fusion's safe. We're out there talking to the NRC in these public meetings. And so I'd invite our participants and anybody else watching. The June 7th NRC meeting is our next one. You can log on just like this and watch our presentations showing safety and how we determined to mitigate safety. Basically, we see fusion as just as safe as existing medical isotope facilities or accelerator facilities, and are pushing for the regulatory environment to be in that way. Fundamentally, fusion will be as safe as a large industrial, power plant. Not it's completely different risk portfolio than a nuclear fission power plant.
And I would just add to that too.
Yeah. Okay.
Yeah, I think Andrew covered some of the parts, but tritium is not as though it's an unknown material. People are surprised when we tell them, if you see an exit sign that glows or watch that glows without electricity, that's tritium. We know how to handle tritium. We know how to do that safely. We take it very seriously at CFS, and so we will be thinking about what is the necessary requirements for handling. But the important thing is to understand it is a low-level waste. So it's very different than when you're thinking about uranium and plutonium and the dangers that come with those and the long-lived waste there. We're talking about materials that will need to be managed for 12 years, decades, and then they're available. And then we have lots of places that are available from, as Andrew said, where we handle this from a medical facilities where the same materials are produced and have to be managed and handled and disposed of properly. So we know how to do this. And so we take it very seriously, and we will continue to do that, but it's not an unknown. But I do think, one of the things that makes fusion so attractive from an environmental and safety perspective is that the fuel is deuterium and tritium. You're not having to think about being tied to a pipeline that has to be where you're at. You can site your facility anywhere you want. It's because you can get the materials delivered in, and you're not worried about some of the safety risks with the hazards that come with if you had a more radioactive material on site that would be non-proliferation concerns and things like that. So.
Great. Dr. Benson, I was just wanted to give you an opportunity to have a final remark.
Yes. Anyway, thank you very much. Yeah, I mean, there's an absolutely tremendous amount of work that needs to be done. We're very excited about, getting, net positive energy, but there are many engineering issues. Building a fusion power plant is complicated, and so we believe the government has an important role it can play, particularly in the identification of cross-cutting technologies, materials, for example, fuel cycle management that would be beneficial for all these companies, and we really look forward to working with the private sector and academics to make this happen.
Great, thank you so much. I'd just like to extend a big thanks to Andrew, Jennifer, and you, Dr. Benson, for sharing your expertise with us here, and everybody else who's stuck with us as we did cross the top of the hour. Appreciate your attention and hope that you found it interesting and useful. And we look forward to continuing the conversation. Thanks, everyone.
Thank you, Doug. Thanks, everyone.
Thank you.